Okay, and we are on. Hi, everyone. Happy New Year and happy new high masterclasses for everyone. uh, Today, to kick off the year with a bang, we have André Rodrigues with us. He is here to talk about live Synoptics Built with railML. Am I right, André?
Yes, but
Like
no.
in the movies. So, Andre has been quite disappeared for some time. I guess it was
Yeah,
like
2 years. Hello,
two
everyone.
years. Yeah, it's been a
Yeah,
long time. I
I've been
remember we
missing,
did like
I believe, 2 years and a half.
yeah.
Um,
I
but
guess it was 2 years and a half. I remember one you did by Christmas time.
yeah,
It-
uh,
a
yes,
group
yeah,
one.
yeah.
Yeah,
It was, it
yeah,
was. I remember
yeah.
that.
It was quite a fun high masterclass. If you want, you can check it on the playlist of high masterclasses on our YouTube channel. And yeah, Andre is going to start his presentation, but before he starts, let me just say the things that I do always at the beginning of these high masterclasses. Uh, Andre has wrote an article about this topic. You can check it on the next slide. If you can
Now,
put it
now.
if you can put on the next slide, you can see
Yeah,
you can scan this QR
cool.
code
Sure.
that will take you to the article that Andre has wrote, and you also have the link on the description of this video. If you don't want to scan the QR code, you can always just do
Yeah,
it on the description of this video. Um, Before Andrea starts, let me just ask, as I do always, to drop us a like and subscribe to our YouTube channel. We are making quite some changes here at the High Masterclass scene. We don't worry; they will continue to be live every month. So don't worry about that. The High Masterclasses will not end. We are making a little shift on it. Like we are going to be a bit less technical, I should say, but we are going to focus not only on high interactive technical abilities, but also where we can make an impact in our clients. And this is why we brought up André Rodrigues today with us. So,
let's
André,
start.
let's start this. Let's start this. Let's
Yeah.
go.
So, I have been away from the past couple of years in a project that take us to this masterclass today. And I will bring you a bit of we have learned in this project. It was it was a very lucky moment to be present in this project because this is something I am fascinating with since I was a little boy. I don't know if you have the, the same issues as I do, but sometimes when I see some movie, I imagine stuff. What if I'm there, or what these how these are made, or how that are made. So this is what I am bringing you to today. And one of these examples is in this movie, the Taking to the Pelham 123 with Denzel Washington and John Travolta. That in some scenes we have Denzel Washington on the control center room, having this enormous synoptic on the back when we spotted this the trains walking on top of these tracks and changing colors and status and stuff. So is that's what we are talking about today, and how this is made, um, and what was the problems that we find to build this. And yeah, that's it. Let's start it. So railML, what is this? Actually, it's very simply to explain. It's a little bit harder to understand. So this is a standardized railway data exchange format. What is this? This is an XML based file that make all the softwares and all the railways networks around the world speak the same language between them. Okay, to simplify this, railML stands for railways, like XLS. X stands for spreadsheets, in this case Excel, just to give an example. This is like this. So it's the format that all the programs and all the softwares in the railways world work and speak with each other. Just a little bit of history, very fast. This was created in 2002 with a few companies that have, as many others, I believe, of course, the same problems, because each project and each client work with a specific format for their software. So it's quite harder when they start a new software or a new problem for a new client, having to do everything again and again and again and again. So they found a way to speak between softwares and between railways network the same way with the same language. So this is a static data to build and draw the network, the topology of the network in the railway system. Okay, that here we can find how the tracks are built and the sizes and the position of the signals on the tracks and the position of the platforms on the tracks. And here's the information where we can find all of this. This is the file where we can find all of this. Of course, in the end, we have to build a software, of course, to read this system. But since that we have a reader for these railML files, we can read all, because they all work the same way. So the challenge that we found, and I believe everyone that are using railML files have. So as you can imagine, the bigger the network is, of course, the problems will increase. But this XML nesting, it's huge. We can have multiples levels of nesting elements, and these elements speak with each other or are connected with each other in the weird way, in my opinion. Okay, it's quite difficult to get information for a specific object or a specific signal, for instance. Getting all the information needed to paint a signal on the screen, we have to go to 2 or 3 places differently and get information, some information in one place and in another place. So it's kind of difficult to understand at the beginning. Since you get, it's become easier and easier. Okay, but at the beginning, it takes a lot of days, weeks, to understand everything what happened inside of XML file. Since that there are no many documentation online. Of course, railML .org. I will pass away in front. I believe it's the next slide. I talk about that. So this integration issues has some problem, because the data that we receive to paint the status of each object, each signal, if the signal or if the driver have to go left or have to stop, or have to walk or whatever, or if the door are closed or open, each software that gave us this data work different ways, in the different ways. They have different IDs, they have different properties. So we still have to deal with a middle way, or middle software that translates the language from the source of the live data that we will receive, and paint it on the software that we use to paint the synoptics. So as you can imagine, the bigger the project, higher the performance, because in a in a small network, I believe we don't have many of these problems. But imagine if we have 100 vehicles working and walking every day. This will lead us, I believe, as so um, 500 and 600 events per second happening all the time, constantly. So this brings a performance risk and the performance problems all the time. So we have to deal with it. And of course, computers. This is for the computers. This is very very expensive processing all of this. So in terms of UI, as I said before, the railML only have a few informations about the network, so the position of the signals and the size of the tracks, but nothing more. So if we have to draw a signal to show if the vehicle can go, so I have to stop, or I have to turn left, or I have to turn right. This is not in railML file. railML file only position the element on a static position. The status that we receive from the live data, we have to deal with that later. We have to build components, some UI components that receive that. We have to receive the data, translate that data to in order to the objects can show the correct status of a signal of a crossroad. So um, this is a huge problem when we have a lot of objects, of course, and bigger the once more bigger the project, harder it takes to deal with this all of these events happening at the same time. So let's pass to the practical example. I believe it's easier to understand having an example to show all of this. I bring you today a very, very, very simple synotic for we can example like this. It could be a detail of a station, and what we have here. I don't know. Can I have a mouse in here, John? I don't. So
A
this was
mouse in here?
yeah. Yeah, you don't see my mouse, right?
Yeah, we can see your mouse.
Oh, cool. Cool. Perfect. So um, this is why we shouldn't have to wait 2 years and a half to do this. So in this synotic, we can find an example of what we can extract from a railML file, and this is this list. In this example, of course, in the background, this is a XML file with a lot of data, and to build a synotic, a visual synotic to an operator operates on a control center. Um, this is what we can extract from one example railML file. So in here we have 4 tracks. You will not spot it right away, but I will explain in a bit. We have 2 platforms. This is represented by these 2 yellow dots. The 2 switches. This is 2 blue dots that represent the interceptions of the tracks. So one switch, of course, have origin node and the left and the right. So the switches always have 3 branches. And we have also 4 signals represented in red in these red dots. So tracks, how can we get this information? This is once more, it's a copy paste of a very small block of code inside of railML file, but this is one track item. So in this case, this railML file will have 4 of these, okay, because we have 4 tracks. For the track 1, we have these elements. Of course, these have a lot of stuff, but for now, let's focus on the essential. So One thing, and this is very important, all the elements on the railML file is referred or are referred to a net element. This is what NER stands for, net element. Okay, this is net element ref. So the track 1 actually is the net element 100. Okay, this is the same. When we spotted an NE100, that's the track 1. Okay, this is what we have to focus. Another properties that we have to deal with is this track begin and track ends. For example, we will not use this. This will be needed when we have trains walking on top of the tracks, and we have to know where the train starts. If they appear from the left or from the right. In the railway, there is no left or right. There is another terms, but it's not the purpose now. So for the tracks, we have the track begin and track end. This is the elements that represent the begin and the end. And in the example, we will need these 120 of length of the track. So this track have 120. In this case, it's just pixels. It's not meters. It's not kilometers. It's just pixels to facilitate the demo. So for the track 1, we have to paint this, and the coordinates that we found on the XML documentation, on railML documentation, work like SVG. I don't know if you are aware of SVG, how SVG work, but it works the same way. So we have axis, X and Y. So left to right, it's the positive X coordinates, and top to bottom, it's the positive Y coordinates. So in this example, as you can see, this each square have 50 pixels. Okay, so the coordinates of this track is 50, 150, and this is like the 50 on X and 150 on on Y, sorry, and the other point of the track is 170, 70, and 150. Since this is horizontal line, the Y it's have the same way, the same value. Sorry, so 170, maybe it's something like in here. No, I don't have the line here, but 150 is here, 200 is in here, so this is 170. So this is a very simple track. Of course, we have more complex tracks. In this case, we have curves on the track. Of course, in the real world, could not exist these curves. Okay, we may have a straight line. This is only in the synoptic world, in the 2D world. We have to draw these like this. So each curve, each point have each specific coordinates or pair of coordinates. So each one of these coordinates represents the stop or the beginning or the end or the points in the middle. The same for the track 3 and the same for the track 4. So this is the 4 tracks that we have. So a little bit difficult, but I try to bring you the easy example I found to show you. And this is how the signals position work. So this work for the signals and platforms also, they works all the same way. And almost network objects works like this. Okay, the crossroads works like this. The signals works like this. 90% of the objects on the network works like this. So they have a place where we find signals information, and of course we have 4 of these, so we will have 4 of these items. In this case, we are just checking the S778 signal. This is the ID. Once more, as I said, always referenced to a net element. In this case, the net element 100. The other thing we have to realize is this intrinsic chord that we have here. And this is the percentage position inside that net element 100. What it means? The net element 100 have 120 pixels long, as we spotted in the previous slides. So this signal is positioned on the 83.33% of the net element 100. This is quite difficult to understand, but I will try to show you. And this is where the information of the signal, of the position of the signal is. So once more, for each signal, each crossword, each wherever, we have coordinates to position the element in the 2D world, in the synoptic world. And how can we get this information? Of course, the software that deal with these synoptics already do this for us and position this for us, but we need to position the signals where we want, not where the software wants. So let's try to understand how this works. So the signal that we are talking about is this one. As you remember in the beginning, I showed you there was 4 signals, 1 in here and 3 in this track, but let's focus on this one. So the Y position, it's simple to understand because this is an horizontal line and all the dots are on the 150 Y position, right? This is in this line, so it's easy to understand. So the coordinate Y, it's Y equals, oh sorry, miss a 0. I have to add a 0 in here, sorry guys. So the coordinate X, we have to calculate it. How? So we know that the intrinsic chord that I spoke you about earlier is 0.8333 percentage of the track. So since the track have 120 long, is 120 long, so the length of the track is 120, so the signal is on the 0.8333 percentage position on the track. So 0.8333 multiplied by 120, sorry, is 99.996 pixels, approximately 100. So this position on the grid is, of course, the 50, that is the coordinate of the track. This is this one, of course. Since we are dealing with these coordinates, it's always from the 0 point. Even if we are inside the track, it's always reference to the 0 point in here. So this position, this point that is 100 pixels inside the track is 50 pixels, that this is the start of the track, plus 100, that is the position from the start of the track, this one that we calculated. So 50 plus 100, it's 150. That's why this signal is in this position. This is kind of weird to understand at the beginning, and this is a very, very simple example. Of course, if we have a signal on the diagonal in here, for instance, it's quite difficult to calculate. It's not that easy. It will deal with trigonometry and so on and so on, and so it's kind of hard to understand that. But don't bother. There are plenty of software to do that for you. You don't have to calculate this and perform all of these calculations. There are plugins to do that. Don't bother. It's just to understand where these coordinates come. Okay. So now we reach the point that we already extract all the data from the railML file. We know the position of the signals and we know the position of the platforms, but now we only know that coordinate X and Y. Now we have to create a software to read that synoptic, to read that railML file, paint a synoptic on the screen, and then on top of it, add an additional object to represent the signals. This is multiple examples of what a signal UI could be. Uh, for instance, we have a very simple one in here with the base and the post and uh, two yellow circles that imagine represent turn left or turn right, something like that. So railML don't have this. railML just have the position where this signal is. So on top of it, we have to create a software to deal all of this with all of these objects and paint on the screen in order to an operator in the control center can have access what's happening on the network. And one example of it, it's a very simple example to draw a synoptic. In our example, with the 4 tracks, we have 2 platforms, as we saw in the beginning, that were placed something in here. But now we have these 2 platforms, and we have these 4 signals in the specific position where the red dots are at the beginning. But as you remember, we only know with the railML the position on top of the track. So in this case, we need an editor to reposition all of these signals and all of these platforms and all of wherever, crossroads and so on, in order to position in a way that trains could walk on top of these tracks and not mess with the position uh, and not hide the signals in order to operator could have and could spot some errors, some problems on the network. And that's it. Sorry for the extension, but it was just a little bit of what we have dealing from the past couple of years. It was a huge project, an amazing project, rewarding project. It was very cool to work with it.
Yeah. And thank you for the presentation, Andre, and thank you for the ones that almost stood by till the end. And yeah, by taking what you were saying, Andre, if we wanted to do a masterclass about every topic that you covered on that project, we would have like masterclasses for 2 or 3 years, guaranteed. So
Believe me, this is, as I said, this is very, very, very simple example of what we have to deal with. We can, on top of it, we can talk about only for tracks. Maybe we have 5 masterclasses.
yeah.
And on top of it, talking about sections that is parts of the tracks that could have states, and that could maybe lead us to another 20 masterclass.
Yeah.
So
Yeah.
it's a different world that I'm used to work. So I'm very pleased to work with this. It's awesome to work with it. So
For sure, for
I
sure.
hope you enjoy it. If you have some questions, please ask us. No
Yeah, yeah,
problem.
yeah. I was going to talk about that. If you have any type of question that you wanted to ask Andre about this topic or regarding any
Another
rail
one.
topic that you may find by watching this high masterclass, please drop it on the comment section of this video. Me, Andre, or everyone at Interactive can see it and answer you straight away. And yeah, don't forget to check Andreas' article and stay tuned for the next High Masterclass. If you have a topic that you want to suggest for the next High Masterclass, please also drop it on the comment section of this video and we will take it into consideration. So with that said, thank you, Andre.
See you in 2 years. No, I'm not.
We-
I hope
I
not. I
would-
hope not.
yeah, see you in 2 years, André. So bye bye.
Bye, guys. See ya.
Bye.